We have seen satellites, we've seen various planets and bodies that are in space, and the question that comes into play is how do they move between each other in space? And this is where orbit analysis comes into play, where first our goal is to unpack the following. What is the shape of a specific orbit that is made by a satellite around a central body? Another question that will be asked is how fast is the object that is the satellite in a specific orbit path relative to the central body? This is actually proposed by some particular dude that we're going to talk about currently. And finally is what is the relationship between the radius of the orbit made by the satellite and the period it takes for it to make one revolution. First, describing the shape of an orbit, we need to take into consideration first a central body and a satellite. In this case, we call it space junk. And this space junk or satellite tend to have a specific stable orbit path, and in this case this is focused on it not being able to fall towards the central body, and so the satellite maintains a speed for a particular radius of orbit, and this requires small boosters or thrusters, rockets, to counteract the friction of thin atmosphere from the central body. Otherwise, this might lead it to be in an unstable orbit and as a result crashes into the central body due to its gravitational force field. Focusing on speed, this is dependent on the mass of the central object or body and the radius of the satellite's orbit. This velocity is derived from the circular motion, and this is expressed as the square root of the gravitational constant multiplied by the central body's mass divided by the radius of the orbital part. And this is shown in this particular formula, and we're going to derive this formula in our specific equation 3 of the Kepler's law. This law was proposed by a German astronomer called Kepler, which derives the laws of planetary motion, develops 3 conclusions that explains the true orbit of planets or any body orbiting around another body. Now we're going to look at this in 3 parts. One is the shape, what it is, and also look at how the speed is influenced in different orbit paths, and finally the relationship between the radius and the period of that specific orbiting object. The first conclusion that addresses the shape looks at it in terms of the orbiting object around a central body. In this case, it was concluded that each planet moves around a central body in an orbit that is an ellipse, not circle, with the sun or the central body at one focus of the ellipse. The second conclusion is based off of observations that Mars speeds up as it approaches the sun and slows down as it moves away. This shows that the straight line joining a planet and the sun sweeps out equal areas in space in equal interval of time. The final conclusion comes from the average radius relationship with the period, where in this case we see that the radius cube is directly proportional to the period squared. Therefore, the constant, which is Cs, in this case focuses on the frame of reference of the sun or the central body, is equal to the ratio of the radius cube and the period squared. Now, how are we going to be able to derive the radius of the orbit and the period relative to the orbiting object? This can be derived from first finding the equivalence between the gravitational force magnitude and that of the centripetal acceleration made by the orbiting object, and therefore by cancelling out the masses of the orbiting object and the radius, we're left with our velocity, which we derived to be equal to the square root of the gravitational constant multiplied by the mass of the central body divided by the radius of the orbiting path. Therefore, this shows relationship between those two parameters, and this leads us to how it is connected to the period, where period is equal to 2 times pi times r divided by the velocity. Therefore, by rearranging the equations, we should have our frame of reference of our central body to be equal to the product of the gravitational constant multiplied by the mass of the central body divided by 4 pi squared, or equal to the ratio between the cube of the radius and the period of the orbiting object's path. This second part here is focusing on the orbiting object, while the first one focuses on the central body. Therefore, in conclusion, in summary, we have that we are able to determine the orbit of the shape's orbit, which is ellipse. And then the second part here, we're able to determine how fast the path is relative to how slow the path of the orbiting object is relative to the central body. And finally, we're able to determine the relationship between the radius and the period, alongside deriving the velocity of the orbiting object based on the central body and the radius, and finally looking at the frame of reference of the central body, which is represented as CS, in this case focusing on the sun, and this is based on the mass of the sun multiplied by the gravitational constant divided by 4 times pi squared. Hope you found this really informative. Please hit a comment down below. Let me hear your thought about this particular video about Kepler's laws and how this focuses on orbiting objects around a central body. And I hope to see you all on the next one. Remember that show notes and illustrations are found on our website at www.dijomerit.org. All the same, stay smart as always and believe in yourselves.